Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about the dynamics of current in an LR circuit, mainly the growth and decay of the current in LR circuit. So, first of all, what is this LR circuit? It is called inductor resistor circuit. In physics, you have been familiar with this circuit diagram. So, this one will look something like this. You have a resistance R with an inductor L, the battery from where the voltage will come, and the switch which is called the key. So, this is positive, this is negative, so the current flows like this. So, this is a LR circuit. So, now what is going to be the dynamics of the current in such a circuit? So, basically when the current flows, you will see that, and mathematically it will be shown that your current reaches a steady state once the switch is on, and when the switch is off, the current does not instantaneously goes to 0, but there is a decline and slowly it reaches to 0. This is exactly what you may have seen, that when you switch off your power source of the laptop, the indicator bulb there, you will see that it is still on while your switch is off, and slowly at one point it then stops blinking, because the power was there and slowly it decays to 0, and till it decays to 0 the indicator is on. So, here let us start with some definition. So, this L is the inductance of the coil, R is the resistance, the coil is connected to the battery, of voltage V through the key, which can be read as switch. This is K. Now, what happens in the on position? So, you put on the switch and you get what is called the on position. So, the current will flow through the coil, and when this current starts to flow, there will be an electromagnetic force which will induce across this L. And according to this law of electromagnetic induction, this EMF will oppose the voltage, and as a result of which there will be a voltage drop across R, and which will also oppose the applied voltage. So, if that is the scenario, then at any time t, di dt, this is the rate of increase of the current. Now, the potential difference across the inductor, this depends on the rate of change of current passing through the inductor. So, mathematically you can write if V1 is the potential difference across the inductor that depends on the rate of change of current passing through the inductor, rate of change of current passing through the inductor, and potential difference across the resistor, that is equal to I into R, which we name as some V2. So, your total V, that is equal to V1 plus V2, which is L di dt plus IR. So, you get a differential equation L di dt plus IR equal to V, and you have to solve this differential equation. So, either this is a first order linear differential equation, either you can use integrating factor or straight away you can do the separation of variables because this V is a constant. So, what you do is you write like this I can write as minus L times di dt is equal to IR minus V. So, I bring this to this side and this to this, and now you separate the variables, you get di by IR minus V equal to dt by L with a negative sign. I take this R common, so di I minus V by R equal to minus dt by L. So, I will cross multiply and I will get the equation of the form di equal to I minus V by R, that is equal to R by L with a negative sign dt. We integrate both sides. So, this is from time t equal to 0 to time t equal to t, and this is initially there is no current and going to some value I. So, this is just log of I minus V by R. This is minus R by L t, this is from 0 to t, and this is from 0 to I. So, if we substitute the values, it is ln I minus V by R minus ln minus V by R, which is equal to minus R by L t. This can be written as ln I minus V by R divided by minus V by R equal to minus R by L t, which implies I minus V by R divided by minus V by R equal to e to the power minus R by L by t. And this will imply I minus V by R equal to minus V by R e to the power minus R by L t. And this gives I equal to V by R minus V by R e to the power minus R by L t. And if you take V by R common, then 1 minus e to the power minus R by L t. This is the current at any time t. Let us now look into the alternate solution. So, we have the equation of the form L di dt plus IR equal to V, which I can write in the form di dt plus R by L times I equal to V by L. Now, this is of the form dy dx plus px into y equal to some q, which is a first order linear. And we know that we have the integrating factor, which is equal to e to the power integration px dx. So, here the value of p is r by L and value of q is v by L. Both of them are constants. So, your integrating factor I dot f is just a notation equal to e to the power integration r by L dt in this particular case, because the independent variable is t. So, we have e to the power r by L t. So, that is our integrating factor. So, the next step is you multiply this differential equation both sides by the integrating factor to the power r by L t into r by L into I equal to v by L e to the power r by L times t. So, this can be written as d dt of I times the integrating factor. So, if you expand this in u into v, you will get this, and that is equal to v by L e to the power r by L t. So, the separation of variables gives you e to the power r by L t dt. So, this will give me I e to the power r by L t is equal to v by L e to the power r by L t divided by r by L plus some constant. So, if we take at time t equal to 0, there is no current, so I equal to 0, and this implies 0 equal to v by L. This cancels, so v by r plus constant. So, basically your constant is equal to minus v by r. So, if I substitute back, I will get I e to the power r by L t, which is equal to v by r e to the power r by L t plus constant, which is minus v by r. So, I t, I just divide by e to the power r by L t. This is equal to v by r minus v by r e to the power minus r by L t. So, if I take v by r common, 1 minus e to the power minus r by L t. So, this is the equation which now represents the current. So, now let us look into the numerical solution. Let us see how the solution behaves, and for that I will be using Microsoft Excel. So, I already have the file open. You have the equation in this form. So, I have put the initial value as 0, your value of V to be 20, R is 3, L is 50, and the H is 1. We will be using this formula, the Euler's formula. So, this is your time and this is your current. So, initially at time t equal to 0, the value is 0. Here I give an equal increment. This, the value of h is 1. So, I drag to some 100 values. Yep. And to calculate this, which is equal to I0 plus h times, h is a constant, so I put dollars multiplied by f of I0, which is this expression, only I is replaced by the initial condition. So, V, which is 20, again this is a constant, minus I multiplied by R, which is again a constant. So, I am inserting dollars, and this whole thing is divided by L, which is again have a constant value. So, you calculate this one cell, you got the value, and you drag it to the next 100 cells, rather 99 cells. And you get some value. So, now you have to plot it. So, you highlight all the calculated values, go to insert, go to this chart section, find the scattered diagram and choose this. So, this is the figure. So, here I can just change the title to growth of current. So, you can see that it starts from initial value 0 and slowly it is growing and ultimately reaching a steady state. Now, as we see the graph which gives the growth of the current, which is similar as we got in our Microsoft Excel. So, if you see, the growth of the current is given by V by R 1 minus e to the power minus R by L t. And while solving the equation using Microsoft Excel, we have taken the value of V to be 20, the value of R to be 3, and initial condition, obviously it starts from I equal to 0. So, if I calculate V by R, it is 20 by 3, which is approximately 6.667. So, for large t, means as t becomes large, then we see that IT goes to, so e to the power minus R by LT as t becomes large, this tends to 0. So, it tends to V by R, and the value of V by R is 6.667. So, which is now confirmed by the numerical graph, numerical solution represented in the graph. You can see that this value where it tends to as your time becomes large is approximately equal to 6.667. Let us now take an example. A series LR circuit having a resistance of 20 units and inductance of 8 units. is connected to a DC voltage source of 120 units at time t equal to 0. So, what is the current in the circuit at time 0.6 units? So, you have a resistance, you have a inductance, and this is connected to a source. This is your R, this is your L, and inductance is 8, your resistance is 20. This produces a 120 volt units. So, the formula you already have the formula which says that the current at any time t is given by V by R 1 minus e to the power minus R by L into t. So, the value of V is 120, the resistance is 20, 1 minus the resistance is 20, the inductance is 8, and the time is 0.6. So, if you simplify this, minus 1.5 and this is equal to 6 multiplied by 1 minus 0.223 units, which is equal to 6 into 0.777 and 4.662 units. Let us now look what is going to be the dynamics when you switch it off. So, now you have the key position off. So, when you switch off the key, it was from the position on position. So, from the on position you have switched off the key. So, your steady value was V by R. So, what will happen? So, we are going to find the dynamics. What will happen when your current was at V by R? So, once the off position, then no current flows, and the flux will reduce gradually. This will result in the drop of voltage across the resistor of resistance R and the induced EMF L di dt across the inductance. So, ultimately your voltage V will come down to 0. So, if we now use this in the differential equation, initially we have this V equal to V1 plus V2, which is equal to L di dt plus IR. This was in the on position. In the off position, this becomes 0. So, your equation becomes 0 equal to L di dt plus IR. So, now you have to just solve this equation that L di dt is plus IR equal to 0. Separation of variables gives you minus IR. This is di by I equal to minus R by L dt. So, the initial value is from here 0 to t, and from here initially the value of I was some capital I, which is V by R, and it is going to reach some I. So, if I integrate this, I will get ln I from V by R to I is equal to minus R by L t, and this will give me ln I minus ln V by R, that is equal to minus R by L t, which is ln I divided by V by R is equal to e to the power R by L t. This implies I by V by R is equal to, this will be I by V by R e to the power minus R by L by t, and ultimately I t is equal to V by R e to the power minus R by L t. So, this is now the solution of the differential equation when in the off position of the switch. So, as you can see from here, as your time becomes large, then your I goes to 0. So, let us quickly see the solution of this in the Microsoft Excel. So, we have now di dt is equal to minus R divided by L, your time, your current, this is 0, and we put some value 7, and let us calculate this one. This is equal to this plus 1, and drag it to say 100 values. So, let us make this 21 such that I equal to V by R, which is 7. So, initial value is 7, and then this value is equal to I0, which is this, plus H times, which is 1, plus, sorry, this is a constant. So, I make this the dollar multiplied by minus I0, so a negative sign, multiplied by R, which is a constant, divided by L. And we drag to the next 100 values, and if we plot this, you press shift and highlight all the values, go to insert, go to the scattered diagram, and this one. So, I will just change it to decay of current. So, you can see it starts from some steady value. So, this is the point where your switch is just off, and then slowly it decays to 0. So, as I was saying that in the decay of the current, it will start from some steady value. This is the point where you just switch it off, and then it slowly decays and goes to 0. So, this is going to be the dynamics of the growth and decay of current in an LR circuit. In the next lecture, we will be talking about the rectilinear motion under variable forces. Till then, bye bye.